All right. So far we have talked about the Poincare transformations, and also we talked a bit about symmetries at the classical level and how they result in the conservation laws. And also we discussed the fact that the theories that describe nature, they have to be relativistic, like Maxwell theory. So we have learned about classical relativistic theories. Now today we want to talk a little bit about when we include quantum mechanics. We want to construct some relativistic theory, relativistic quantum theory. See what is the implications of the requirement that we have this symmetry, Poincare symmetry. So what we do in quantum mechanics is that we have a wave function, and that wave function gives us the probabilities for the results of experiments, for the observations. And when you have a symmetry, what happens is that those symmetry transformations act on the wave function as unitary matrices or unitary transformations, so that they present the norm of the wave function, so that they don't change probabilities. If it is a symmetry, then that symmetry shouldn't change the observables like probability. So therefore we want to find the unitary representations of the symmetry group, and these unitary representations usually are very big, but they decompose into different blocks, which we call them irreducible transformations. So we want to identify those irreducible representations of our symmetry group, and those irreducible representations correspond to different species of the particles. What is the meaning of this irreducible representation? It just tells you that all they form the set of states that by symmetry transformation they can be transformed into one another. And you're already familiar with this concept, having these representations from the ordinary non-relativistic quantum mechanics. So we can do some exercises to remember what these irreducible representations are, and then it's easy to understand how this generalizes in the relativistic. So we want to go, so yeah, this goes to U. I'm sorry, when you do that. So we want to, let's consider some simple example, which is the case of a spin in non-relativistic quantum mechanics. So there we talk about rotations as a symmetry, and then we identify the unitary representations of the rotation group. So what is the rotation group? Is SO3 or SU2. Locally they are the same. They have a different global structure. Locally they are identified by some commutation relation. So they have generators. And we find representations for this group. In particular, we have the simplest non-trivial representation that we find is the spin 1/2 representation. So this is identified by eigenstates. So when we find the representations, they are characterized by the eigenvalues of J squared and, for instance, JZ, and then the eigenvalue of the the eigenvalue of the J squared is S times S plus 1. Is it correct? Yeah. And then JZ goes from minus S to S. So now if we consider S equals 1/2, then we have we only have two possibilities. We have plus and minus. And so what does it mean when we say this spin 1/2 is an irreducible representation? What it means is that if we do rotations, we can go from plus to minus. So this set of states forms a complete set that transfers into each other. So we cannot go outside this set by doing rotations. Now, we want to consider an explicit example of taking the spin plus 1/2 along z direction to the spin minus 1/2. Let's find one unitary transformation that takes plus to minus. So I want to use matrix notation. Plus 1 is 1, 0. And I want a matrix that takes 1, 0 to 0, 1. Sorry? Okay. So what is that matrix? Let's call that matrix, I don't know, A. A times 1, 0 equals 0, 1. We can immediately write one answer to this. So this is one possible choice. And many of you, I think, found this. Of course, there are infinitely many solutions to this equation. So we want the A to transform 1, 0 to 0, 1, and we want it to be a unitary transformation. So this is one solution to this equation. What size? Yes, has to be 1. Or in matrix notation, it has to be 1. Thank you. Yeah, so this is one answer, which is the, well, I guess this is sigma y, or sigma x probably. Of course, there are other solutions. We could also take sigma y, which is, I think, minus I 0, 0, or maybe I minus 1. And what is the interpretation of these matrices? For instance, this one is sigma x. What it is doing is doing a rotation of pi along the x-axis. And that rotation of pi along the x-axis takes the eigenvalue in the z direction to the eigenvalue to the along minus z direction. What we could do, obviously we could do a pi rotation along any other direction that sits in the xy plane, and therefore there are an infinite number of them. So here I have explicitly written 2 of them. Now as you can see here, if I act by sigma y on 1, 0, what I get is I times 0, 1. So these two differ only by a phase. And this is true also for all those infinite family of rotations that do this job. They are all related by doing the following. I can do a rotation along the z-axis, and then after that I can do a rotation of pi along x-axis, and then undo the rotation along the z-axis. So if I conjugate this sigma x, by an arbitrary u z theta, then I get that infinite family. So this rotation by along z-axis, what it does is that it multiplies, since we have a spin 1/2 state, the uz of theta is equal to e to the I theta over 2 and e to the minus I theta over 2, 0, 0. So this matrix is going to be e to the minus I theta over 2, e to the I theta over 2 times 1, 0 times this one. Minus I theta over 2. One side. Which is what? So here I get e to the minus I theta, the minus I theta, 0, 0. So this is just e to the, no, that's it. So this is the infinite family of transformations that we have, which takes us from the spin plus to e to the I theta times the spin minus. And again, these are just rotations that I can do along different directions. I take plus c to minus c. Okay, so this was just some explicit example of perhaps the simplest irreducible representation of the rotation group. Now, what other element of this space-time translations are we dealing with? There is also boost. So let us also consider an example of the boost transformation. It's still non-relativistic quantum mechanics. So here we were doing rotation. So now we want to take a boost, or we want to find a boost operator whose job is to do the following. So we have unitaries, and then there's a Hermitian matrix B, Hermitian operator B, which is the generator of boosts. And what it should do for us is that if we consider an eigenstate of momentum operator, So this psi p is an eigenstate of the momentum operator. If we act by this u of v on that psi p, it should have momentum p plus mv. So we want to explicitly define what is this boost operator in this non-relativistic quantum mechanics. So what is the requirement? Therefore, the requirement is that if p acts on u of v, acting on psi p, this has to be an eigenstate of momentum operator with eigenvalue p plus mv. So therefore, we should have this relation.
In the exercise, when you wrote psi, you meant wave function?
Yes.
Oh, I thought you meant spinner, so I wrote the spinner representation. It was not specific.
Yeah, I meant wave function. I mean, everything was in the about non-relativistic quantum mechanics. So therefore, what is the condition that we want to satisfy? We want to have u dagger of v, p u of v, to be equal to p, this is the momentum operator, plus m times v, right? So if we write it explicitly, we want e to the minus I v dot p, p e to the I v dot p is equal to that. So this expression, we can expand it in powers of v. So what we get is p plus iv. Let me now use the indices, or maybe not. Okay. Commutator of p and v dot b plus I squared over 2 commutator of p and v dot b and v dot b, and so on. Now, if we want this expansion to match with this result, then here we have p on both sides, so these two match, and then we have only the first power of v here. So this is the term that has the first power of v in it. So by comparison of these two terms, we conclude that the commutator of p and v dot b has to be equal to m dot v. That is also a factor of I. So that tells us that the commutator of p and b, let me put it now in the component notation, pi and bj is equal to minus I times m times delta of I and j. Which means that bj is m times the x operator j plus anything that commutes with p. So any function or any vector function of p would do the job. For instance, I could have it here let's write Pj f of p square. However, what this does is that, well, for instance, if this f was a constant, that would do a translation for us. So if I just want to do a boost, then if I don't want to change the position of some wave function, then I would just set this to 0. And then I get just m times xj. Any question? So now we can ask the following question. Imagine we want to find a boost that takes a state with 0 momentum to a state with some momentum p. So this is kind of similar to what we asked there about the spin. What is the rotation that takes us from the spin up to some other spin? There we asked about the spin down. And we saw that there are many different rotations that do the job. And they differ by phase. Now here we can ask the same question. If we start from momentum p equal to 0, what is the boost that takes me to the state with momentum given by p? And that is easy. It's just a boost with parameter v given by momentum p divided by m. So at least this is one transformation that does the job. Explicitly for that one particle, this is e to the I. Now this p is the number, not the operator, right? So this is a lowercase p, this is a number, and this x is the operator. So this is the unitary transformation that transfers the state which is addressed to the state that has momentum p. Now we could ask, are there other unitary transformations that do the job? For instance, we could do different boosts. Say I do a boost. Let's consider a very concrete example. Suppose this p, we want it to be a momentum along x direction. So say this p is some px times x hat. Right, then our transformation would be really e to the I px times operator x. Now by x I mean really x, the first component of the position operator. Now what we could do is to combine different boosts. Say I do a boost along y direction, then I do a boost along x, and then I undo the boost along y direction. So I conjugate this with boost along y with some other parameter u. So I do u dagger similar to there, u dagger y of u, ux of v, u y of u. Right, so let's try to do an analogous thing. However, what happens is that since these boost operators, they commute with each other, boost operators in the non-relativistic theory, so we find that there is just x and y. So here we have explicitly, we have e to the minus I mu times y, e to the I mv times x, e to the I mu times y. But this is the same as the original one that we can say, e to the I mvx. Just because the generators of this non-relativistic Galilean boost are commuting with each other. So what does it imply? It implies that if we want to, in a non-relativistic theory, if we want to talk about representations of the space-time transformations, momentum and rotations and boosts, what we can do is to identify the states by the momentum and their spin. And then the transformation properties of these states are relatively simple. For instance, if I want to act by some general transformation on this, some combination, some rotation and a boost. Again, I'm talking about non-relativistic boost. That action is relatively simple. So first of all, if I want to act by rotation, combination rotation and a boost in a non-relativistic theory, or even in a relativistic theory, we can always decompose it into a boost followed by rotation. So say I want to have a rotation along some axis, and then and then I want to have a boost acting on this psi of p and sigma. So these are the psi of p and sigma is supposed to be a particle with some momentum and some spin, and I want to understand how it transforms when I act by these transformations. The psi of p and sigma, we can write it as the action of a boost, and as we saw here, there is a unique boost that takes it from the rest to this momentum. So we can write it as u of p over m, a boost with parameter p over m acting on psi of 0 and sigma. And then an action of another transformation on that is simple because what it does is that first of all we can just combine these two boosts. So we have u of v, u of p over m, psi 0 sigma. But the combination of this, again, because the structure of this boost, Galilean boost, is very simple, it's just the action of a single boost. So we just get u of theta, u of v plus p over m acting on psi of 0 and sigma. And this is nothing but psi with the rotation acting on p plus mv, and the same rotation acting on the sigma. So in a sense, when we talk about the particles with the spin in non-relativistic quantum mechanics, adding a spin to whatever we had before is very easy. Basically, these two, the action on the spin and the actions of the Galilean boost, they don't talk much to each other, so we can just act by rotations on the spins, and then we do everything that we have been doing for the particles without the spin, as before. However, this is not going to be the case in relativistic, in the relativistic theory, because boosts do not commute in a relativistic theory. That introduces a bit of complications when we talk about this unitary representations, irreducible representations of Poincare group. So what happens is that now in a, so far these were non-relativistic. In a non-relativistic theory, we have a non-trivial commutation relation of the boost operators commuting into rotations. This is called Thomas precision. Something that as I go to a smaller velocities, it becomes negligible. So what does it imply? What it implies is that now if I try to do a similar thing, if I try to do as before, I diagonalize my momentum operator, I have a state with definite momentum, and I know that boosts are going to change the momentum of the particle. Therefore, as before, we would like to identify the states of the system by some continuous variable, which is momentum, which is the eigenvalue of total momentum. And then some internal degrees of freedom, which when we talk about single particles, this would be something similar to a spin. Now, if we want to do something like before, write the psi of p and sigma as a boost acting on the state on a particle at rest, in the case in which we have a massive particle, or if it's not massive, if it's massive, if we want to write it as a boost acting on some standard, the standard state, so some u of some lambda of p or L of p, some Lorentz transformation which depends on p and act on, suppose it's a massive particle, so I want to transform it from the rest to that momentum. Then this choice of u here is not unique as before. And this non-uniqueness introduces some complications when we talk about when we want to actually construct that transformation. I won't go through the details of this. You can find it in the notes. It's a nice story, but it might be a bit too formal to go through here. So that let me just summarize the final conclusion. We want to classify these irreducible representations of Lorentz group or Poincare group. The classification is based on based on two parameters. So first of all, we have m squared, which is the eigenvalue of p squared operator. So we consider p squared, which is p0 squared minus spatial momentum squared. And first of all, the representations are parameterized by the eigenvalue of this p squared operator, and that's why they call it mass squared. So p squared acting on psi on an irreducible representation gives m squared times psi. Actually, maybe if I want to be consistent, I should write it as minus p0 squared and plus p squared, because I'm using mostly plus signature, and therefore this should be minus m squared. So these representations are classified by the mass squared of the particle. And there are two cases to be considered. One is when m squared is non-zero and positive. So here we are dealing with massive representations. And even though the transformation properties become a bit more complicated compared to the non-relativistic case, the classification is identical. And the reason is kind of obvious. The reason is that if we are dealing with massive particles, we can go to the frame in which the particle is at rest, or it is moving slowly, and therefore there the transformation should reduce to the non-relativistic transformations, and the classification should also reduce to that. This classification gives us particles with the spin, which are integer numbers. So we cannot continuously change that by going from small velocities to large velocities. So for massive particles, we essentially get the same classification as we had before. We have mass of the particle and we have the spin, which are the representations of SO3 group. So we have S, which can be 0, 1, 1, and so on. Or the other possibility, and this is the one that doesn't exist when we discuss non-relativistic physics, is when there is zero mass, and therefore there is no rest frame. And there the particles are classified in terms of their helicity. And helicities are, so the helicity is an eigenstate of SO2 group. This is the group of rotation in perpendicular to the momentum of the particle. So since we are in 4 dimensions and we have 3 spatial direction, the spatial directions, the rotations perpendicular to the momentum is going to be a rotation in a plane, whose group is SO2 group. And then there are also some more global considerations that restrict the eigenvalues to be integer or half integer. Basically, the reason is that the rotation by 4 pi should give 1. So again, we have helicities that can be half integer. So these are the 2 sets of possibilities that we find. Two sets of possibilities for single particle state. So again, these are the things that basically they were familiar, we were dealing with before in a non-relativistic theory. These are the things that are new in a sense. And what we do to construct a quantum theory for these degrees of freedom, so what is our goal? We want to identify what are the irreducible representation, which we call them particle. Then we introduce creation and annihilation operators for this particle. So we have A's and A daggers, which depend on the momentum and sigma, this internal degree of freedom, which is a spin or helicity, depending on that. So we have A's and A daggers for any representation that we have, and we want to construct interactions between these particles, which are Lorentz invariant. Now again, there's another nice story there that you can find in Weinberg. I'm not going to go through it, but the upshot is that in order to construct a Lorentz invariant theory, we have to package these creation and annihilation operators inside fields, inside quantum fields. Like in the massive case, for instance, you have already seen in QED that we have the electron field. Or if you have some scalar field, massive scalar field, Klein-Gordon field, they will be, these creation and annihilation operators will be packaged there. And similarly for the massless field, so if you consider spin 1, for instance, there will be A mu, again, the photon field that you have seen in QED. And in order to find the relativistic theory for interactions of these particles, what we do is that we construct a quantum field theory, which is based on an action which depends on these fields, which themselves depend or are constructed out of this creation and annihilation operators for this. So after a longer story, we get to this quantum field theory that you are studying. And what we are going to do here is, instead of going through the details of why this is the case, we are going to accept that this is the case. That in order to have a relativistic theory, which is compatible with quantum mechanics, we have to work with the quantum field theory. Write an action in terms of some fields which transform on the representations of Lorentz. So what we want to ask is that what is a relativistic theory for gravity following these rules? And also following the observations. So we want to construct a phenomenologically viable theory of gravity, which is relativist. So that's the goal of the lecture. Any questions so far?
You wrote that if m squared is greater than 0, then we should consider SO3. So can you say that SO3 is the little group?
Yes, it is a little group. Yes. Yeah. The little group is, so the idea is that, for those who you haven't heard of it before, the idea is basically this, that we first diagonalize the momentum. So we characterize the wave function by the eigenvalues of momentum, which is this p, and then to characterize other internal degrees of freedom, what we do is that we go to some reference frame by doing boosts. and then we do find the representations of the Lorentz transformation that keep us within that reference frame. So here, for instance, in the non-relativistic theory, I said that we go to the rest frame, and then there what we are dealing with are just rotations. In a non-relativistic theory, so if we are in this situation, we are basically going to do the same thing. We go to the rest frame, and there we identify the remaining Lorentz transformation that keep us in the rest frame. Those remaining Lorentz transformations that keep us on that reference frame are called the little group, and those representations are going to be classify the possibilities for sigma. Also, in the massless case, we do the same thing, a similar thing, except that that reference frame that we choose is not the rest frame. It's a frame in which the particle has the prescribed momentum. And since it has a prescribed momentum, the Lorentz transformations that preserve it should be somewhat restricted. So for instance, it's kind of obvious that if I go to a frame in which the prescribed momentum is along x direction, then the rotations that I do that preserve it are rotations in the YZ plane. That's why I get SO2. There are some extra things, but eventually if we want to have discrete representation, that's the only thing that remains.
What is the last sentence that you said? That if you want to do discrete things?
But you can ignore it because I haven't told you the details. But when you go to this, the little group is the component of the Lorentz or Poincare transformation that preserve that reference frame that you have picked. Now what happens is that it's bigger than SO2. There are extra elements, but if you want to have non-trivial eigenvalues of those extra components, then you will get continuous representation, meaning that representations that, unlike here when we have discrete set of spin states or helicity states, they have continuous values.
They are unphysical.
They are. We have no evidence that they exist in nature. In principle, they seem to be possibilities. These are called continuous spin particles. Some people studied them.
In condensed matter, I'm sure they should exist.
In condensed matter? Why are you so sure?
Everything exists there.
I'm not sure about this case. Notice that here we are discussing Lorentz invariant theories. There you get many things which are Lorentz non-relativistic, Lorentz breaking, because you have a prefed reference frame.
Okay.
In a sense, you have many more possibilities when you discuss condensed matter physics, because Lorentz symmetry is very restricted.
And in condensed matter, you have particles which are not actually particles, but they are invented to describe the phenomena. For example, axions, magnons, and phonons. They are not actual particles, but they are just invented to describe the phenomena.
Yeah, although in a sense, you can think of every particle that we talk about in the same way. There was this idea that there are fundamental particles and non-fundamental particles, but a more modern point of view is that there is no such thing as fundamental particles. Everything is effective description at some at some energy or at some scale, the description is going to change. Okay, so I don't have that much time, but I say a few words about where we want to go. Nevertheless. So we want to talk about relativistic gravity. So what is the goal or objective? Our objective is to construct a relativistic theory for gravity, which is compatible with the Newtonian gravity, because we know that Newtonian gravity is very successful to describe a lot of phenomena. So in a non-relativistic limit, we want to recover Newtonian gravity. So what is Newtonian gravity? We can formulate it in terms of the Newtonian potential that is given, but that is related to the mass distribution rho in the following way. And then there is a Newtonian force on every particle which has mass, which is given by minus m times grad phi. So minus m times grad phi is the force. And this is an instantaneous force. So if you have two particles, they move, the Newtonian theory predicts action at a distance. When I move things, they instantaneously affect each other, which is of course something that is not acceptable in a relativistic theory, because equal time doesn't have is not a well-defined notion in relativity. It's observer dependent. So of course this is not acceptable in a relativistic theory. We want to come up with a relativistic version of gravity, and in a relativistic theory, what we understand is that if we want to have forces between particles or between two sources, those forces have to be mediated by some other particle. So if gravity is causing a force between two massive objects or massive particles, that should, in a relativistic theory, that should be because of the exchange of some degrees of freedom in between them. And the whole question is that what is that degree of freedom that is responsible for the gravitational force. And then here we have the list of possibilities. So we are going to go through this list and pick the one which is the correct choice. And then write a relativistic theory, or the other way around, right? Go through the list, write the relativistic theory following our rules of writing interactions, and see if that relativistic theory gives the right predictions compatible with what is. So we can already understand many things without too much work. For instance, we know that gravity is a long-range force, meaning that it gives if you have two massive particles, it gives a force which goes as 1 over r squared, or the potential that goes as 1 over r. That already tells us that we have to be on the second line here, because if we have massive particles, if m squared is non-zero, then it leads to a potential or a force that falls exponentially at distances larger than 1 over n. So since that's not how gravity looks like, therefore m has to be 0. Of course, we have not measured gravity at infinite distances, so you can always ask, how do we know this m is not tiny but not 0? It's a valid question. For simplicity, I take it to be 0. In some cases, you see that there is a continuity, meaning that if you assume that it is non-zero, and then you took the mass to be smaller and smaller, you will recover the answer for 0 mass at short distances. However, it's not that continuous, because, for instance, if you, that's true for the spin 0 and helicity 0, but as you go to higher spins, then it becomes less and less continuous, because, for instance, as you can see here, this here we have on the top line, for spin 1, we have a spin 1 representation of this O3, which has 3 degrees of freedom, right? 2j plus 1, for j equals 1 is 3. But if we go to the bottom, we have only 2 possibilities, helicity plus and helicity minus. So there is a discontinuity as you take mass to 0. And these discontinuities will show up in various ways. So therefore, there is some degree of rigidity in this limit. So let us stick to m equal to 0. Now, then we can ask about the choice of the helicity. First of all, we want it to be some integer, not half integer. We want this to be a boson rather than fermion, because we have macroscopic gravitational fields produced by macroscopic objects. It means that there is a non-zero vacuum expectation value for this. We have situations in which we have non-zero vacuum expectation value for this gravitational field. Or in other words, we want to have large occupation number of this force carrier, which describes a classical gravitational field. So therefore, it should be a boson. It cannot be a spin 1 like a photon, even though this equation, if you look at it, it actually looks very similar to the equation for the electrostatic potential, which would give rise to the Coulomb force or the Coulomb potential. And the reason is that there, of course, we know that this electrostatic potential, it will merge and combines with the vector potential to form the photon field. So that is how it becomes a relativistic theory. However, we know that in electromagnetism, like charges repel each other, while like charges in gravity, which are just like masses, positive masses, they attract. So the spin 1 is also excluded as an option. So the easiest choice, in fact, even without saying this, would be the spin 0, the simplest possibility. So we are led to consider the following theory, the theory of the spin 0 particle. I again call it phi, which is coupled to some source 4 pi gt, where t has the property that in the non-relativistic limit becomes minus rho. And we already have have a guess for what that object has to be. It has to be the trace of the energy momentum tensor that we talked about in the previous lecture. In a non-relativistic limit, the 0, component of the stress energy tensor is just well, in general, it is the energy density. In the non-relativistic limit, it just becomes the mass density. And that dominates over other components of the stress energy tensor. So if I calculate the trace, so this T00 in the non-relativistic limit is dominated by mass times number density, and the trace would, in this limit, would actually be just rho, the mass density. And it is relativistic. It's the trace of a Lorentz tensor. So the theory, the first proposal for a relativistic theory for gravity that we can consider is a theory of a scalar field coupled to matter field, which gives that equation of motion. So I can write it's an action for it, minus 1 over 2 kappa d phi squared plus phi times T mu, the trace of the stress energy tensor. And this T mu depends on the other fields that exist in my theory. So here it should really be phi and other fields. Let's just collectively call them psi. So this T mu is the energy momentum tensor of those other fields. And this is effectively an interaction. In particular, if I have a free field, this gives me a cubic interaction between phi and those fields, those psi fields. And then our task will be to see what would be the predictions of this theory, which we will discuss in the future lectures. Any questions?